Hello and welcome everybody to this introduction to algebraic geometry. We start with the definition of affine algebraic sets. These are defined to be the zero sets of polynomials in n variables over a algebraically closed field K. And of course you remember that the affine space a to the n is defined to be the set of tuples a1 to an, where each ai is an element of our field K. And n-dimensional polynomials f define maps from the affine space a to the n to K just by plugging in the points of an into f. So let's have a look at a subset S of K x1 to xn. And we denote the set of common zeros of S by Z of S. And sets of this form are called affine algebraic set. Since this is our first important definition, have a look at some examples. We can express the affine space a to the n as an affine algebraic set by writing a to the n is equal to z of the zero polynomial, or we can express the empty set as z of the constant polynomial 1, and we can express every point in a to the n as the zero set of polynomials x1 minus a1 to xn minus an, or we can express subspaces of a to the n as zero sets of polynomials f1 to fr, where each polynomial fi is one-dimensional. For example, if we want to express subspace of A3, which is given by the condition that the third coordinate is 0, we can express the subspace as x of as z of x3. Now note that if we have a set S inside a set T, then we have z of S contains z of t. This should be clear because for a point to be in z of t means that it is a common zero of all polynomials in t. Now t contains s, so this point is certainly a zero of all polynomials in S, which is just this statement. And as a consequence, we will see in the next lecture that we can express every affine algebraic set as the zero set of an ideal in kx1 to xn. And we will also introduce the Zariski topology. So thank you for watching. Stay tuned. See you next time.